Hello, what we're going to have a look at today is something that I did when I was doing my maths many years ago, doing ordinary GCSE maths or O-level maths. And what we did then, we started having a look at something called logs. And surprisingly, at the moment, this is becoming quite important to people. So let's have a look why. Now, what I'm going to look at is a simple idea about a logarithmic system. So these funny things called logs, sometimes called exponentials. And I want to have a look at some of these. We've all seen on the news graphs showing people sort of contracting the COVID-19 virus, and curves start to look like this sort of thing. And very quickly, these graphs become rather sort of stupid because we sort of lose what's going on down here as these numbers become very big. And logs are something we can actually do to sort of explain and show how exponentials work. So let's have a little look and dive into this a little bit deeper and see what we can find out. So let's have a look at a very simple system about what logs are and what we can do with them. So let's have a look at something really simple. And what I want to do is I want to have a look at trying to add up two numbers. And all I'm going to do to start with is I'm going to add simply here, I'm going to put in 2 plus 3. And we're all clever enough to work out that's going to be 5. Okay, let's do 2 times 3. And we're all clever enough to work out it's going to be 6. But if I made this a bigger, more awkward number, I'm going to struggle. So what we can do is something quite interesting and clever. We're going to look at a log. So I'm going to take the log of a number 2. And that's going to give me nothing because I pressed the wrong button. So we're going to go back. Here we go. Log, and here I've got to put in base 10. I forgot that. And I want to put in here 2, and there we go. And I get a number. Right, so that number is, I've just taken the log to the base 10 of 2, and that gives me this number. And I've got here 0.3010. That'll do for the time being. Let's do the same, but this time we're going to take the log to the base 10 of 3. So all I'm going to do is go into my calculator and we're going to type in the same thing again. So log, this time to the base 10, and we want to put it in here of 3. And I'm getting in the number 0.4771. Let's see what we can actually do if we try and add those two numbers up. So let's just do that. That's going to give me 1877. And now what I'm going to do on my calculator is I'm going to do the opposite of the log. And this is written down here as 10x. So we're going to do shift 10x, and I'm going to type in that number. I'm going to type in my 0.7781. And my calculator didn't do that at all, did it? Let's try that again. Let's cancel. Shift that, 10 to the, and it should have taken in my naught, yeah, 0.7781. I've got my numeric keypad on there, it'll work better. And that gives me a number which is 5.9992, whatever, or more approximately 6. What I've done is I have simply added my numbers up and I've got an answer. So logs do something quite clever. Now, at GCSE, you've really met this, but not in this quite form. Let's suppose I want to multiply two numbers together. And my two numbers together are going to be x squared, and I'm going to multiply that by x cubed. And we know that if we multiply these together, we basically add the indices, so that's going to give me x to the 5. Now let's look at what we did. If I did x squared, which is x times x, and I multiply that by x times x times x, I indeed get x to the 5. So in some ways, I've done the same thing here. What I've done is I've said, well, what is 2? Well, 2 is 10 to the power of 0.3010. And I know that log 3 is the base 10 of 0.4771. And if I simply add those together, I get 10 to the power of 0.7781, which is approximately equal to 6. It would have been better to be 6 if I had actually put all the digits in. But I was trying to make my life a little bit easier. Right, so we've met this with indices and what it can do. We've discovered that the rules of indices are as follows. The rules of indices is that if you want to multiply two numbers together, we simply add them. If we want to divide two numbers, then we subtract them. And if we want to do anything to the power of, then you can multiply them. Let's make some more sense of this. Let's see if we can make it a little bit easier. Looking at some indices, let's start off with something like, let's go down here a little bit. Let's go for x squared. Well, we know that x squared is x times x, okay? I could have done this a different way. I could have done this with 2 squared. It's going to be 2 times 2. And we can all work out that's going to be 4. Let's do x cubed. X times x times x. Or we could do 2 cubed. 2 times 2 times 2 equals 8. Let's go the other way. Let's go x to the 1. Well, that's going to be easy. That's going to be x. 2 to the 1. Well, that's going to be on this simple idea 2 times, well, nothing. So it's itself. So it's just going to be just 2. Now the one that catches people out, x to the 0. X to the 0 is 1. 2 to the 0 is 1. In fact, anything to the 0 equals 1. Let's go further along. X to the minus 1. Where do we go with x to the minus 1? Well, minus in this case means 1 over. So this is going to be 1 over x. Doing it with the 2, this is going to be 2 to the minus 1, which is going to be 1 over 2, which is a half. And do it once more. X to the minus 2 is going to be 1 over x squared. That's all the minus sign means, 1 over. So this 2 to the minus 2 is going to be 1 over 2 squared. And 1 over 2 squared is 1 over 4. Okay, let's see what else we can discover. If I've got x to the half, this is one you just have to know. This is simply the square root of x. Do it with our 2. 2 to the half becomes the square root of 2. Not one I can easily work out without the calculator. X to the third. Well, you might spot this one. This is the cube root of x. So therefore, 2 to the third is going to be the cube root of 2. And so it carries on. Let's mix up those nasty minuses that we had at the top with these at the bottom. What happens? Well, we've got x to the minus a half. I said that minus means 1 over, so this is going to be 1 over the half, and that was the square root of x. Do it with 2. 2 to the minus a half is going to be the same as 1 over the square root of 2. And if we carried on that idea, x to the minus a third is going to be 1 over the cube root of x, and 2 to the minus a third will be, you've probably guessed it, 1 over the cube root of 2. So we've got lots of interesting relationships with these exponential functions. Right, so we've got these exponentials, and we can do a whole series of sums with them, and you get to sort of practice these in school a fair bit. Let's have a look at just a couple of these. Let's take x to the 5th times x to the 7. Well, we know we simply add these. So this is going to become x to the 12. If I've got x to the 7 divided by x to the 5, then this means it's going to be x to the 7 minus, we subtract when we divide. So 7 minus 5 is going to give us x squared. Yeah, well, they're going to do some horrible things to you in a maths test, aren't they? So let's have a look and see what nasty things they could do here. Well, we could be given something like x to the 5, and we can divide that by x to the 7. Well, there's no real harm here. This is just going to be x to the 5 minus 7, which is going to give us x to the minus 2. Yeah, we can cope with that because we already know what x to the minus 2 is. This means 1 over x squared. Well, let's try another nasty one. Let's try x to the 5th. Let's divide this one by x to the minus 2. Ugh, not looking so nice now. So we've got x to the 5 here, minus, and then it's minus 2, which is the same as plus 2. So this becomes x to the 7. Right, okay. We're getting the hang of these bits and pieces. So exponentials can be used to make some of our numbers a lot smaller. Rather than writing in lots of x's here, I can just write x to the 7, and I know it saves me some time and some effort. So where do all these nasty things come to, and how do we make some sense of what's going on? Well, when you are at school, usually some of the better lessons are when the teacher says you can use the calculator. When I was at school, I didn't have a calculator. It wasn't because I was that poor. It was because they hadn't been invented then. It's a bit sad. And instead, I had one of these things, a slide rule. And they're wonderful things. They've got bits and pieces you can slide along, and then you can move the slide along. You can read the answer. Right. I don't want that. I don't want to try and use it. Although, go on then. You persuaded me. We'll just have a quick look at what we can do with this slide rule. Because what it can do is something quite interesting. So let's look at this scale here. And it's got numbers 1, 2, 3, 4. And you'll notice they're getting closer and closer together. And in fact, we find that that's something about this that does something. So let's line this 1 up with the 2. And if I move this line along, I can say that 2 2s are 4. There we are. Doing my 2 times table, 2 times 2 is 4. Let's move this along to the 3. 2 times 3 is 6. Oh. 2 times 4 is 8. 2 times 5 is 10. 2 times 10 is 20. Okay. And if I move this slide along a little bit further, so it's with the 3, I can say that 3 times 2 is, yeah, you've guessed it, look, 6. Put the cursor over it. 2 3s are 6. 3 3s are 9. 4 3s are, now it gets a bit more difficult. You have to try and count it up. But we've got 10 here, and then the next one's going to be 11, and the next one, 12. 10 3s, there we are, 30. And it works with any multiplication table. Okay, so what's funny about one of these? Well, let's take my slide rule to bits, and we'll have a look. Zooming right out and trying to get the light just right, the distance from 1 to 10 is the same as the distance as 10 to 100, and is the same as the distance from 100 to 1,000. Okay, so this is called a logarithmic scale. And if we try and have a look and see what this does, this can sometimes give us an idea of what's going on in nature. Now, we're hearing that the COVID-19 virus has got something called exponential growth. Well, it means that probably it's going to double. So we're going to see a graph looking something like this. Well, let's see if we can make a bit more sense of this. So let's try and draw it out a bit better. And I've gone to squared paper here. And let's see if we can draw a graph out. And what I'm going to do is I'm just going to draw a very simple graph. And I'm going to try and draw it properly. Really will have to zoom out here to the maximum amount. And let's try and draw a line along here. Right, we're going to try and draw out some sort of exponential graph and see what happens. So this is going to be 1, 2, 3, 4, and so on. I'm not going to bother with any more because I know I'm going to have problems. Let's go on with 1. And we'll put the numbers going along the side here, because we're going to immediately discover a few problems when I try and draw a graph. So let's do a graph of what I'm going to do, x squared. I'm going to actually do 2 squared. So let's try one of these. So 1 squared is going to be 1. 2 squared is going to be 4. 3 squared is going to be 9. And then 4 squared is going to be 16. And we can see this graph is looking horrendous going up here. And the next one's going to be 25. I'm already off the graph. Could I make this a little bit simpler? Could I try to make this graph have perhaps a better scale on it? Well, yeah, we could try something else. Let's try something really stupid that you're told not to do in school. Let's imagine we set this at 1, this one at 2, this one at 4, and then 8, 16, 32, 64, 128, 256. Let's see what would happen then. I've got sort of a squash scale here. So let's have a look and see what I've got. 1, 1 is 1. 2 2s are going to be here 4. 3 are going to be 9. It's going to be somewhere about there. 4s are going to be 16. That's going to go there. 5's going to be 25. Oh, it's going to be somewhere like that, I think. And 6 6s are going to be 36, just barely over the line. 7 7s are going to be 49. It's got to be somewhere around there. And 8 8s are 64. 9 9s are 81. And then 10 10s are 100. Yeah, it's got to be somewhere around there. And this graph is now doing something else. It's doing something else rather stupid. This graph is now going the other way. So what would happen if I could try and get these graphs? So it's not a real graph number, but these numbers are better along here. Could we then, in fact, try and get another graph that's going to put some sort of straight line? And this straight line is a log graph. And we can see interesting relationships. So let's have a look at this. So this time we're going to try something interesting with my scale. And what I'm going to do is I'm going to use a rather weird scale on this side. So let's draw in my axis, and I'm going to draw in my 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10. It's getting hard, so 11, 12, 13, 14, 15, back there. And I'm going to put 16 in there. So here's my 16, and let's just try and put in some other numbers that will be useful. This is 1, this is 2, this one's going to be 4, that one's going to be 9. So let's have a look and see what's going to happen if I draw in this sort of graph. And if I draw in this graph, 1, 2, 3, 4, I'm only going to go up to 4. 1, 1 is 1. And we're going to get, that's right, I'm being told to move it up a little bit. Right, okay. 2 2's are going to give us 4, which is going to be about there. 3 squared is going to give me 9. 4 is going to give me 16. And we're seeing that this is making a better graph. It's not quite straight line, but we've got something going according to this. Now, this is because I'm doing a square and I'm not actually rising up exponentially, but we can look at growth doing something like doubling. So let's see what we can do with this. So if I take another piece of paper and we try and do a graph of how things are going, and we're looking at populations doubling every few times. So let's take some sort of doubling to see what's going to happen. So we're doubling, we've got 2 goes to 4, goes to 8, goes to 16, goes to 32, goes to 64, and so on. It's doubling each time, and we're seeing with this a graph going up like that. If I can change this scale, we can start to get this to follow a line. Now, how's this important? Well, if we look at our cases of COVID-19 at the moment, let's see what they're doing if the number of cases are doubling. So we can have, if you like, a line with these figures on. And if your number is slightly lower or slightly higher, then we can see that, well, people could mistake this for going on to something else. Let's draw this in as a logarithmic function. And what we should see is if it is logarithmic growth, the numbers will be following a straight line. And if we're doing better than this curve, then our numbers hopefully will become lower than that. And we can see then we're not on logarithmic doubling, but in fact, we're doing better. When we look at viruses growing, we look at something called R0. R0 works for viruses, it works for bacteria. And what we're looking at is how many people this one person can infect. If this person can infect someone that's going to sort of give us just one other person, then our graph is going to look like this. It's going to stay steady. If this is going to be less than 1, then it's just going to die out. But if we're now on a number such as 2, this means that each person that gets the virus infects 2 others, then we're going to see the graph doubling and going up like this. And worse, if it's trebling or more than that, our so-called super spreaders, then we're seeing our graph shooting up horrendously, and it's only going to be a few weeks before everyone's got the whole virus. And maybe some countries will decide that that's the way of trying to do things. Maybe because they can't afford to shut things down. And in which case then this graph will be exponential. But in fact it won't be. Now, why don't we get an exponential graph working like this for the entire population? Well, let's take an example of the UK. And the UK has got something like about, let's say, 60 million people. Okay, so let's draw a graph with 60 million people on it. Here we go, 30 million, and we'll just do this with simple millions. If I've got a graph, which is going to be here, days going along the bottom, we can't get a graph that looks like this. This is an exponential graph, but we can't, because once we get to 60 million people, we're actually going to run out of people to infect. We can't infect anymore because they've already been infected. So our exponential graph might start off exponential, but then it's going to sort of run out and then die out. Because once that happened, all the people have been infected. And we know, we see on the TV that we're trying to get these graphs now to go lower, to take longer, and hopefully, if we can then get them to level off and die out, then no more people will get the virus. So exponentials can be sort of quite useful ways of trying to sort of explain what's going on. They can make numbers that are big look a little bit smaller, so we can sort of compare them a little bit better. So I hope that's given you a little bit of an idea about exponentials. I haven't tried to go into too much detail, and I haven't tried to draw these things really accurately, but in fact we can, and we can use wonderful spreadsheets to do this and record all the numbers very accurately. So there we are, some stuff with indices, exponentials, to try and perhaps explain some of the graphs you might see on the news these days. And stay safe, and I'll see you next time. Bye-bye.